Very good morning. Welcome you all to the NPTEL course on electrical distribution system analysis. And today we'll be talking about optimal location and sizing battery energy storage systems. In distribution system, as you know today, it is more or less accommodating maximum amount of renewable energy, which was not there in the past. And hence it is quite important to also integrate storage devices to store the excess energy which is available to us through renewable integration sources. Now, when you just concentrate on BESS technology, how it is going to work. So, first of all, as you could see, this is my storage device. Okay. And as you all know that the storage devices are in DC, and then we have a power conversion system through a DC switch, and then there is a AC breaker and there is a AC transformer, and then it can be connected to my AC source or sink. Now, for example, if you like to have some DC load to be catered through your storage, so probably you can take it a terminal to cater your DC source or DC sink. Now, BES technology transforms electrical energy into storable electropotential energy, and it has majorly three components: sources, converter and storage. And power conversion system is an important component. Control and monitoring system as well as battery are the key component of your storage devices. Now, monitoring and control system ensure safe and optimal performance, preventing overcharging or over draining of batteries. Now, there are different type of storage technologies today available across the world, and they are popularly known as flow battery, lead acid battery, lithium ion battery, flywheels, compressed air energy storage, ultracapacitors, superconducting magnetic energy storage. But depending upon the applications, we can use different storage technologies. For example, in case of flow battery, it is non-toxic, high energy storage, flexible control, as well as low maintenance. Now, in case of lead acid, it is quite heavy, less durable, rapid aging of high temperatures. Lithium ion, which is quite popular, which is high efficiency, lightweight, suitable for home and EV uses. So, and hence, today, lithium ion batteries are quite popular in renewable integrated distribution systems. Now, why we go for storage? The main reason for going for storage is to provide load shifting during off-peak to peak times, because during off-peak hours, the storage technology can store the energy and discharge during peak hours, which also reduces consumer energy bill in time varying pricing situations, because during peak hours, the cost of energy is very, very high. If you have a storage technology, probably you can store the cheaper energy and discharge during the high cost energy price. Storage technology also enhances systems flexibility and reduces energy cost. Now, we can carry out time shifting, demand management, renewable smoothing, cost reduction, peak demand reduction, ancillary services, off-grid stabilization, frequency regulation and voltage control. All these applications are possible through a BESS technology. Now, in case of low and medium voltage system, it reduces cost and manages network operation efficiently. It avoids need for costly distribution infrastructure upgrades, significant power loss reduction and better system control, and policies and regulation guide BESS use with specific requirements for deployment. Now, when we go for certain technology with energy integration, especially deployment is influenced by the level of renewable energy integration within the network, and the BESS, the battery technology, with long operating life helps utilities delay major investment in distribution infrastructure, such as constructing new circuits and installing additional transformers and overload sensors. Now, why we can delay? What is the reason for delaying the investment for substation or substation constructions or transformer installations? Now let's say your transformer, which is currently catering X MVA to the consumers, and tomorrow if you have more customers connected to your distribution system, which is X plus 10% increase, let us assume, which is 1.1 times X. So the transformer need to be replaced by a new transformer which is of 2X capacity and which is very, very expensive. However, if you can put bit of renewable energy integrated or even at least battery technologies, those batteries actually can cater your excess load without increasing the substation size. So that's why, though battery is not free of cost, but there could be a economic calculation may be carried out by the distribution companies to make sure that this battery technology is economical compared to upgrading the new substations. Now, BESS stores electrical energy during period of low demand or excess supply and releases it if during peak demand periods. An established communication link between utilities and the storage technology is necessary for observability and controllability. This approach allows for better energy management, ensuring that energy stored during the period of excess renewable generation can be utilized when it has greater economic value. Now, this is one of the example which very clearly highlights how actually we can store the excess PV energy in BESS from, for example, 9 a.m. to 4 a.m. So, this is the period, all right. And it says that utility uses generator and PV systems to meet 24 hours load demand, and excess PV energy is being stored with my battery. So, this is the kind of excess energy which is available to me, and they can be charged through my battery and can be discharged during the peak hours. Now, if you go for BS energy from actually, if you like to discharge the battery now between 5 p.m. to 12 a.m., which is considered to be evening peak. So, BS energy is used from 5 p.m. to 12 a.m., reducing dependency on the generator after 9 p.m. and saving energy cost. So, what you've done basically, you captured this segment through your battery and you perhaps actually discharge to different zones so that the cheaper renewable energy can be utilized during peak hours. Now, from the company or large business perspective, how this battery technology is going to help you. Now, high energy consumption leads to increased operational cost for businesses. So, the BESS technology can help reduce this cost by minimizing energy charges and tariffs imposed by the utilities. For example, a distribution company says your peak energy is costing you 10 rupees per unit, and probably otherwise it is 2 rupees per unit. So, you can plan and have your own installation of storage technology so that you can avoid purchasing energy during costly hours, that is 10 rupees per hour. Now, BS also enhances supply reliability during electricity outages, which is crucial for continuous business operators. Now, let's say if the utility decided not to go for procuring energy during peak hours, and probably those disturbances you can avoid having your own generation which can cater during any disturbances. Now, demand charges are typically based on the peak demand rather than the actual energy consumed. So, by deploying battery technology, businesses can save peak demand, thereby reducing demand charges very significantly. For instances, a demand charge of rupees 3 per kilowatt can be reduced by saving peak load using BESS, resulting in substantially monthly saving. Now, look at one more interesting example. Now, for the business houses, so this is basically your demand curve, okay, which is keep on, and you could see there are multiple peaks. These are two peaks, and because of which you need to meet 400 kilowatt requirement throughout the day's operation. So, this is the demand charge we need to pay for peak requirement. So, it says that the demand charge is going to be rupees 3 per kilowatt month. So, at peak demand, if it is going to be 400 kilowatt, then we have to pay the peak demand charge, which is close to rupees 1200, okay, or it could be $1,200 or whatever it is. Now it shows that the demand charge before peak saving a total cost of rupees 1200 per month. So one has to pay 1200 rupees per month because of meeting out the peaks. Now let us say one more scenario. If you could achieve the peak saving through your batteries, means you need not get those peak from your utility, but you can locally manage. So let's say you can manage with 300 kilowatt, okay. So then your cost become 900 rupees. So you are saving approximately 300 rupees per month. It could be $300. This is just a numerical example, but there is huge saving. So it illustrates the demand charges after peak saving at the total cost of rupees 900 per month, resulting a saving of rupees 300 per month. So how we could save it? Because this energy, the excess 100 kilowatt hour or 100 kilowatt of peak requirement, can be met through your discharge from your battery technology. All right. So that is how actually we can save your monthly demand charges or peak demand charges. Now, from off-grid or microgrid perspective, remote areas often face inadequate electricity supply and rely on alternative sources like diesel generators, which are costly and have high environmental impact. So today across the country, irrespective of the reliability, whether you have energy or not, for the safer side, I mean, we do have additional diesel generators as a backup. Let's say even 5 minutes fail in a day during summer, we need to have your generators. Now, which is not a good option, okay? So, diesel generator is not environmentally friendly. So, I strongly do not recommend to operate your diesel generator. However, you can have your battery storage technology probably which can be charged through your own renewable energy sources, which is one of the best option, or at least from the grid you can charge and keep it for discharging. So, the development of off-grid and microgrid systems incorporating renewable energy resources after cheap and environmental friendly alternatives. So, in off-grid and microgrid system, the battery technology can serve as a base load energy sources, because anytime it can give you X kilowatt hours of energy, significantly reducing the reliance on costly fossil fuel generators. So, perhaps you can altogether eliminate your diesel generator if you have a battery technology. Now, the battery technology also allows generators to operate at peak efficiency, minimizing fuel consumptions and maintenance cost. If you are using still a fuel generator, then very rarely they can be brought into the system until unless the battery is not enough to meet your requirements. Now, this is one more case study. Let's see, as per the off-grid and microgrid perspective, how we are going to utilize. So, it is a charging of actually a battery with fuel generator and excess PV energy. So, this battery being charged based on whatever the energy available through your diesel generator or excess PV if it is available to you. So, this is the amount that you can charge, or you can use your diesel generator to charge it, or maybe a coal plant. Now, so charging of battery with a fuel generator and excess PV energy over 24 hours. Now, what I do suggest here, now illustrate the next example, switching off fuel generator and using BESS energy from 5 to 8 am and 5 pm to 12 pm. So, that means it illustrates the usage of PV and battery energy to meet the load in the subsequent 24 hours period, reducing the reliance of the generator. So, the question here is that you do not operate or mainly depend on a fuel based generator to be available to you, or the grid must be available to you for survival. However, actually you can engage those portions, actually through your battery storage technologies. Now, there is one question that I haven't addressed even today, even at this point of time. That is, we say the benefit of batteries, but we haven't discussed about the cost associated by bringing battery technology to your system. First of all, is it economical? If it is economical, how much? That need to be investigated. So, cost consideration is a very important factor, or LCOE, that is leveraged cost of ESS, energy storage systems. So for that, cost is essential for choosing energy storage systems to meet economic goals, while capital cost often justifies ESS deployments. The leveraged cost of ESS, that is LCOE, is used for evaluating long-term benefits over 25 years. So you consider life of the battery is close to 25 years in general, so 20 to 25 years. Now LCOE allows for easy evaluation of recurring cost, that is maintenance, operation, replacement, and comparison with cumulative saving generated by BESS deployments. So the LCOE can be calculated as summation of Ct plus Om plus Ch times 1 plus Rd to the power minus T upon summation of Et times 1 plus Rd to power minus T. So let us understand what are those acronyms or nomenclatures. Now CT is the total cost expenditure, OMT is the operation and maintenance cost, and CST is the charging cost, because each and every battery life to have certain number of charging and discharging permitted limits, and hence there is a cost associated for each time that you charge. And ET is the discharge electricity in megawatt hour, the amount of energy is being discharged, and 1 plus Rd to the power minus T is the discount factor in year T. Now, choosing the right battery storage technology, the factors for selecting the appropriate BESS vary across technologies and application, and it is crucial to consider the technological and economical values and minimize the cost, reduce energy losses, and make sure that the profit is maximum. Now, whenever you go for battery storage technology installation, there are few questions that need to be addressed before you plan for a battery. That is cost and type of BESS storage. So different technologies that has been explained to you in the just before a couple of slides, those technologies have different cost per unit energy. Okay, so you need to compare which technology and what is the cost, and what is the time frame for deploying the BESS system, that is hours to year. Okay, and sizing of the BESS, which is quite important in terms of kilowatt hours in distribution system, and in large systems probably it could be in megawatt hours. So the question is how much, whether it's 100 kilowatt hour, 1000 kilowatt hour, 2000 kilowatt hour, 10 megawatt hour, and so on and so forth. So the battery technology peak instantaneous power provisions, that is kilowatt or megawatt hours. Battery technology cycling frequency, that is multiple times daily or infrequently. Support for renewable energy, that is solar, wind, or none. And type of application for the battery energy storage systems. And the location of those batteries are quite important, because depending upon the load scenarios, the locations can be identified. Now, evaluating all individual storage applications alternatives in theoretically possible but impractical due to the large number of options. In distribution system, the number of alternatives depends on the number of system buses and BESS installations, making the evaluation process quite time consuming, and hence we have to carry out optimization processes. So the optimization methods are essential to solve the complexity of evaluating all possible storage alternatives. Instead of evaluating each option, optimization tools generate alternatives based on previous evaluation results. This approach leads to the creation of an optimal storage alternative that meets specific optimization objectives and constraints. Now, what are the steps for battery optimization algorithms? First of all, step number 1, identify the application to be served or necessary network support to be provided by the battery energy storage systems. So, what do you expect out of it? Step number 2, formulate the optimization problem to determine the setting and sizing of the battery energy storage system, considering technical and economical constraints. What are those inputs need to be provided? The complete network information and the battery energy storage systems and cost parameters. What is expected to be the output? Optimal operation of the chosen applications. Now moving to the next step, define the objective based on network support needs. Example, minimizing investment and operation cost, power loss and voltage deviations. The constraints such as power flow constraints, battery energy storage system operation constraints, upper and lower bounds on decision variables. And there are different methods available today, probably the classical optimization techniques, that is mathematical optimization, or we can even move to meta-heuristic algorithms as well as some of the AI/ML technologies. The last one, validate the optimal sitting and sizing results with tested real power system networks. So once you get those solutions, you go to the real system, place them and see whether it is performing as you desired before starting the simulation. Now, these are few technical parameters and economic parameters as well as environmental parameters. So, in case of technical parameters, what we do is that we need to focus on power flow constraints, power losses, renewable energy, and then load curtailment or sources, then battery energy storage system constraints and capabilities, reverse power flow. Okay, that means you have a battery, you have a load. Now you, let's say, install a battery of huge size, okay, which is 10 times more than the load. So probably those battery energy when it discharges must go back to your substation, which is quite challenging. System reliability and stability. So these are the technical parameters one has to focus before going for your battery technologies. In case of economic parameters such as what is the investment, replacement cost, operation maintenance cost, load curtailment cost, budget limitation, arbitrage benefits, revenue from ancillary services, and then whether there is some discount given by the government agencies to carry out promoting green energy, implementations. Now, what are the environmental parameters? For example, emission levels, resiliency, land availability, battery disposal and recycling, impact on local wildlife and ecosystems, and noise and visual impact. So, these are the overall scenario. One has to concentrate on what are the technical parameters I have to focus, economic parameters that need to be focused, and environmental parameters that should be kept in mind before planning different battery technologies to be integrated in my distribution systems. Now, when we mathematically formulate it, so the generalized power flow equation, which is mandatory with and without battery. So, this is my power flow equations, the real power and reactive power. They are all non-linear and non-convex. So, with integer and binary variables for locations, distribution planning problem become mixed integer nonlinear programming. Okay. So, anyway, they are nonlinear, but it is mixed integer because of the switching on and off many of the devices within the distribution system, including the batteries. So, these problems can be solved using heuristic techniques, mathematical programming, analytical techniques, and AI, as we discussed earlier. So, there are different technologies, methods, analytical methods, and then you have mathematical optimization techniques, artificial intelligence techniques, and meta-heuristic optimizations, and each one of them have certain merits and certain demerits, and that you need to focus on. Let us work out on a case study which has been published in one of the IEEE transaction on industrial informatics by Tripti Gangwar, myself, and another professor, Premlata Jena. So, this article talks about a bit of identifying the battery locations. Okay. So, first of all, in this system, we have actually created scenarios where PV penetration of buses, 17, 18, 32, 33 with a penetration level close to 80%. And the system consists of 33 buses and 32 lines and has a voltage of 12.66 kV, and the load size is close to 3.715 megawatt and 2.3 MVAR. Now, if you formulate the problem using two-stage mixed integer linear programming, where first one is the approximation 1 and 2 that need to be focused on. So, we need to assume that the nodal voltage magnitude are assumed close to the rated voltage, and the small voltage angle difference of a branch ij leading to the approximation, that is sin theta ij, which is theta ij, and cos theta ij equal to 1. Okay, so cos 0, which is 1, and when theta is too small, sin theta is equal to theta. So these are the two important linearized power flow equations, and then you can create the nodal power balance equation considering the batteries. So then you can also have certain constraints. So this is my energy store constraints and simultaneous charging, discharging, and then status of initial and final energy over a period of 24 hours. So what we consider in the last constraint, if there is a battery, you started with, let's say, X percentage of energy available to you before the day begins, that is my time 1 or hour 0 or hour 1, okay, and then you make sure the whole day cycle gets over, you like to leave the battery at the same state, okay. You cannot achieve many more things by draining out the battery today, and tomorrow you do not have anything to operate because the battery is completely drained out. So it has been assumed that if it is 50% charging state, if you start the day, even during end of the day, you must leave the battery with 50% of its charging. So the objective function is to minimize the sum of power rating cost, energy rating cost, fixed operation and maintenance cost of lithium ion batteries plus grid input cost. So you'll be getting energy from the grid. So there is a cost associated, and the rest will be your battery associated energy costs. So Cp and Ce are the cost coefficient of P rated and E rated energy and power capacity of the batteries. So this is what you see the load data of for 4 seasons. So we have considered winter, summer, autumn and spring, and you could see different load characteristics. All right, and this is the irradiation data of different 4 seasons. So in general, though the magnitudes are different, okay, but as a whole the scenarios are almost same, okay, and these are the cost that has been assumed. So to be very honest, this cost are not necessary to be a binding rule. At that point of time, we try to capture some of the data, and it has been considered, but probably with time, when you carry out your own analysis, you can take the cost data available to you on that particular year. So these are the things we have assumed: the investment cost, and then the fixed O&M cost, assumed lifetime, capital recovery factors, discharging and charging periods, and DOD limits. To the simulation, the voltage variation of 24 hours of the previous system with BESS and without BESS allocation. So this is the initial one, and with BESS, we could see this is how it is going to change. And these are the 4 batteries that has been obtained, that energy rating of 2.78 megawatt hour, 0.46, 4.0 and 0.76. These are the energy ratings, and perhaps these are the power ratings. So 0.19 megawatt, 1 megawatt, 0.712 and 0.7. So totally the requirement of close to 2 megawatt of battery, and with an energy requirement of close to 8 megawatt of megawatt hours of energy requirement. With that simulation confidence, we have moved to IIT Roorkee distribution network, which is quite interesting, and enjoy actually at the end of the conclusion how exciting it is. So we have considered the IIT Roorkee distribution system, and the beauty of IIT Roorkee distribution system that it is purely a microgrid structure, where we have actually source from the main grid, we have diesel generator, we have a lot of PV in the campus, and probably with this simulation we will conclude that the battery can also be installed to optimally operate the distribution system of IIT Roorkee. And we are very happy to say that currently we have 2 storage technologies already installed out of the project grant of Department of Electrical Engineering, Roorkee. Now most of the buildings on the campus have rooftop solar penetrations with a total of 27 locations, and approximately the IITR network has a total load capacity of 6 megawatt and a PV installed capacity of 1.8 megawatt. But this was a very, very old scenario. Today the scenario has changed. The 6 megawatt has gone as high as 8 to 9 megawatt, and the 1.8 megawatt has moved to 2.7 megawatt. Okay, so this is for your benefit of understanding. So when there is a low load in the system during summer vacation or lunchtime, so there is an excess PV available to me during summer when the students are not there in the hostel, so which can be utilized by integrating a battery technology. So most of the time in campus, that most of the renewable energy, they are excessively available to us. So we are not able to fail to store them properly, and hence, especially during the summer vacation, we have seen that the PV generation available to me in most of the hour in the afternoon is more than the load requirement. Okay, so that was the beginning point where we realized why not we go for storage technologies. But beyond, we also explored other avenues through storage technology integrations. So these are the specific, voltage profiles of spring, summer, and autumn that we have obtained, and these are the size of batteries. We have concluded that the rating could be 75, 50, 75, 100, or the kilowatt hour could be 150, 100, 150, and 200. This is our book of IIT Roorkee, and you could see these are the areas where the solar technology is available or the rooftop PV. And these are my smart meters available, and these are different battery technologies proposed to be integrated in the distribution system of IIT Roorkee. And this has been installed close to 150 kilowatt hour. And one more location which has not been mentioned, but in electrical engineering department we do have a 272 kilowatt hour storage already in place. So you could see these two technologies. So this is one and these are the two. So these are the 274 kilowatt hour at electrical engineering department and 150 kilowatt hour in the Mehta Family School of Artificial Intelligence and Data Science. And fortunately, those two sites are adjacent to each other, so few more research can be planned in near future. Conclude, the distributed battery energy storage systems mitigates voltage deviations and defer distribution upgrades, provides robust solutions but is computationally intensive and for large problems. Okay, so load, PV output uncertainties, and battery life cycle impact the planning of battery energy storage systems. Discharging capacity decline with cycles, and future research should address those degradation challenges. So the focus on cost effectiveness, reliability, stability, and advanced algorithm integration for complex scenarios need to be focused in near future. So with this note, we come to an end. Thank you very much.